Okay, so today we are listening to the defense of Viktoriia Chekalina. The title is Computationally Efficient Natural Language Processing Methods Using Tensor Representations. The supervisor is Professor Alexander Panchenko. Okay, let me introduce the jury members. So I will be the chairman today. So my name is Alexey Frolov. I'm the professor of Skolkovo Institute of Science and Technology. So I have defended PhD and doctoral degrees in mathematics. And my research interest lies on the board of information theory, communications, and machine learning. So the defenses were in fundamentals of computer science, theoretical foundations of computer science. Okay, let's keep the supervisor right now. Okay, let me introduce jury members. So Stefan Egger, so from Bielefeld University, is a Heisenberg grant recipient of the DFG, leading the natural language learning group at Bielefeld University. Stefan obtained a PhD in economics on the topic of social learning and opinion dynamics. His research interests are NLP, machine learning, and its applications in the digital humanities and social sciences. Okay, the next member is Andrei Kutuzov. He is an associate professor in the language technology group at the University of Oslo and manager of the high performance language technology project. Andrei received a master's degree in computational linguistics at the National Research University High School of Economics in 2014 and defended PhD thesis, distributional word embeddings in modeling diachronic semantic change in 2020. His research interests are semantic change detection and diachronically aware language models, distributional semantics, machine learning, and large-scale language models. So the next member is Pavan Goyal, so professor from Indian Institute of Technology. He joined the Department of Computer Science and Engineering as an assistant professor in 2013. Before that, he was working at INRI as a postdoctoral fellow. Pavan received PhD from Intelligent System Research Center, Faculty of Computing and Engineering. The topic of PhD dissertation was analytic knowledge discovery techniques and ad hoc information retrieval and text summarization. His research interests are text mining, natural language processing, information retrieval, and Sanskrit, computational linguistics. So the next member is Artem Shalmanov, graduated from MEPFI in 2012 and received his PhD degree in 2015 from Russian Academy of Sciences. His doctoral thesis is devoted to the semantic parsing of natural language texts and applications in information retrieval. Currently, he is a senior research scientist in the NLP department at the Mohammed bin Zayed University of Artificial Intelligence in United Arab Emirates. His primary research interests encompass uncertainty estimation for LLMs and advancement of trustworthy AI, weakly supervised learning, and memory-augmented neural models. Okay, Valentin Malych, right? From Huawei. Valentin Malych is a senior research scientist at MTS AI and associate professor at ITMO University. His field of interest are natural language understanding and deep learning. Valentin graduated from Moscow Institute of Physics and Technology in 2009 and also wrote his PhD thesis there and defended it at Institute for System Programming, Russian Academy of Sciences in 2019. Okay, now the jury members so this was the introduction of jury members. For now, let us switch to the supervisor. So the supervisor is Alexander Panchenko. He is associate professor in Skoltech. He joined Skoltech in 2019, and he is a head of the Natural Language Processing Laboratory. Before Skoltech, he was a postdoctoral researcher in the group of Chris Biemann at the University of Hamburg, Germany, and had a position of postdoc at TU Darmstadt. Alexander received PhD in computational linguistics from University Catholique de Louvain, Belgium. His research interests are computational lexical semantics and argument mining. This is the supervisor and Viktoriia. So let me switch to presentation of Viktoriia Chekalina. So Viktoriia Chekalina graduated from Moscow State University Physics Department in 2014 and graduated from Yandex School of Data Analysis in 2016. She worked at Yandex, CERN, and Philips Research Lab. Viktoriia joined Skoltech in 2019 as a PhD student in NLP Lab and research engineer. Her research interests are efficient large language models and knowledge-based question answering. Okay, so this is the end of the introduction. For now, I will give the word to Viktoriia and recall that, Viktoriia, you have around 40 minutes and I will show if we are close to this deadline, so I will show you. Okay, please.
Okay. So hello everyone. Thank you everyone to coming. My PhD thesis is computationally efficient natural language processing method using tensor representations. I did this thesis into the computational and data science and engineering department under the supervision of Professor Alexander Panchenko. So there is a brief outline of the presentation. Firstly, we are going through publications and briefly discuss motivation, research objective, methodology I've used to meet research objective. And then we are investigating efficient knowledge representation of graph embedding. Then we are investigating efficient representation of fully connected layers. And then we can see how we can apply fully connected layers into the GPT models while training this from scratch, into the models which provide solution for question answering problem, and to the transformer-based BERT and BART models. So there is a publication I've made during my PhD. The most significant, which is better for deploying Python and MATLAB. This publication describes a brief overview of question answering method. Maker memory efficient knowledge embedding representation describes the efficient representation of knowledge embeddings. Retrieving comparative arguments using ensemble method. Retrieving comparative arguments using deep language models. Using pre-trained language models are 3 publications which are related to my participation into the Touche shared task, where I should retrieve the proper passages which successfully met user query. Efficient GPT model provide TTM-based layers and how we can use it inside GPT models. Computational study of matrix decomposition provide comparison of different decomposition methods for transformer models. And the last publication is about our course about transformers, which we held for industry and academia students. So the motivation of my work is the following. NLP methods have advanced over the past few years, and there are 2 points of their advancement. The first one is an improvement in the hardware capabilities for processing and employing large data. The second point is improvement in the architecture of language models. For example, adding transformers into the NLP significantly improve state-of-the-art over the entire set of natural language model tasks. So the significant increasing of the size of the NLP models and of the data leads to the large training and fine-tuning costs. We should discover more efficient methods for working with large data set and big models. There are several ways to do it. We decided to compress data set or model by reducing number of parameters and reduce the number of parameters by represent data into the algebraic form, in a tensor form in our case. So tensor is a multidimensional array in common case, and tensor representation represent data which initially can be a tensor, but uncompressed tensor, as a set of smaller objects, factor matrices, or set of low-order tensor. If we have a task, if we want to compress dataset or model, firstly, we decide in which form we should represent our data or model, and then to fill this form by meaning, by digit, we apply the proper decomposition, tensor decomposition to the data. To obtain efficient knowledge graph representation, we use canonical pleiadic structure, and to apply canonical pleiadic structure, we use a CP-LAS algorithm, which is provided by Calder and Bader. We also provide PyTorch-compatible layers based on tensor train matrix structure, and to obtain this decomposition, we use algorithm with SVD-TT, which was provided by Ivan Asilidis. We apply TTM layer to the GPT model. Calbert is a question answer and retrieval model, and BART models. And when we apply some compression technique to yet pre-trained models, we usually have a drop in quality, and to improve this quality drop, we try to align the decomposition and task-oriented objective by involving efficient information into the decomposition, and we try to select layers inside the models that are more sensitive to compression. So there is briefly tensor notation we are using in our presentation. The first row is a tensor as a multidimensional, n-dimensional object in our case. Then its entry. G is a core tensor, is a factor into the Tucker and tensor train decomposition. Lambda is a diagonal core tensor in canonical pleiadic decomposition, A, B, matrix, and vector. Then goes several product which we can apply to matrix, vector, and tensors. Then mod n product, and then we have several operator we can apply to the matrix. And the last is a mod n matrixization unfolding of a tensor. So since matrixization is a least understood concept, I provide a picture about unfolding or matrixization. So we have a n-dimensional tensor. We select one of the dimension, and among this dimension, we scratch our tensor like harmonic. So for three-dimensional tensor, we can have three unfolding, and every unfolding is represented in this way. So the first chapter is about efficient representation of knowledge graph embedding. In this chapter, we will use canonical pleiadic decomposition. Canonical pleiadic decomposition represents the initial tensor X as a set of factor matrices A, B, and C, and core tensor lambda. So to obtain the approximation of the tensor X, we should select from A, B, and C the vectors with the similar indexes, multiply it by each other. By this multiplication, we obtain tensor with the size with the same of the initial tensor, and add this tensor with the weight which are stored in the matrix lambda. So there is an alternatively square algorithm which provides the solution in which way we can obtain matrix A, B, and C, because to obtain CP decomposition, we should obtain matrix A, B, and C. So we alternatively fix two matrices and update the weight of the third matrices by finding arc minimum of the norm between corresponding unfolding of the initial tensor and this multiplication over these matrices. And we do it until we met the stopping criteria, and we count lambda weights as a norm of the corresponding column of unfoldings. We want to obtain a representation of elements in knowledge graph. So our data is a knowledge graph. What is knowledge graph? Knowledge graph is a set of triples where every triples corresponds to one fact. For example, triple Albert Einstein born in German Empire. Albert Einstein is entity, born in is relation, German Empire is entity. So triple is entity, relation, entity. And this structure, knowledge graph, contains a lot of information, and to use this vast amount of information into the NLP task, we should have good embedding of every element of knowledge graph. So we decide represent knowledge graph as a three-dimensional tensor. We enumerate all possible entity and relation inside the entity and relation vocabulary. And triple is a unit in this tensor which is placed in the intersection of the indexes of the corresponding entity, relation, and entity. So we find embedding of entities as matrix A and relation embeddings of relation as matrix B. We try to apply CP-LAS decomposition to this structure, but CP decomposition provides not very high score. So we decided to apply another version of CP-LAS algorithm without LAS. In this version, we allow deriving update rules under the condition of the exponential family of data distribution. So LAS means a solution for Gaussian distribution. But in our case, we have tensor with 0 and units, and we should use Bernoulli distribution. So we take approach from Hong et al. And in this approach, we can calculate gradients of a matrix A, B, and C of elements of this matrix by this formula. Instead of tensor X, initial tensor, we have another two tensor with the same size as X. This is tensor F. F is an element-wide lossless tensor. Every element of this are described by this formula. And tensor Y is a partial derivative of element of the tensor F with respect to the element M. So here X is element of the initial tensor, M is element of the corresponding tensor which we obtained while we approximate our tensor with our factor matrices. So we firstly count tensor of losses between initial and approximation tensor, and then take partial derivatives over the new element, over the element of the approximated tensor. So this approach, oops. Yes. Okay, it works now. So this is a new algorithm to obtain gradients for the matrix A, B, and A in our case. And instead of other application based on neural network to solve problems of obtaining embedding, where we represent our embedding as an embedding layer in PyTorch and using computational graph to update this embedding, we didn't use computational graph, and because of it, we need less memory than other approaches. So we evaluate our approach on several tasks. The first task is a link prediction task. Link prediction task is when we have beginning of triple, first entity and relation, and we should obtain the completed entity. So we should select the completed entity from the entity vocabulary. We evaluate our approach on the link prediction task on the Facebook 50,237 dataset and WVNRR 18 dataset. We compare our approaches to other approaches. The best score comes from very strong baseline Quarto. Quarto provides hyperplane-based embedding of knowledge graph, and they reach very high score. And our message in the last in this table, it's very competitive among to other. But if we can see to the memory, we need to use our message. We can see that our message needs less memory than other, especially than Quarto. Then we go to the more biggest data set with several millions of triples. I didn't mention all data set from previous slide are on English language. Now we evaluate either on English or in Russian. So we use Wikidata 5M dataset based on English Wikidata and Wikidata 4M dataset based on Russian Wikidata. And we create several models, several light-weighted models, which we can map into the one GPU. Several models like complex sparse and transient sparse provide sparse version of PyTorch embeddings. And corresponding to this model, our method provides the best score on link prediction dataset, but simple consider into the memory, into the using gigabytes to the complex sparse method. The next evaluation was on downstream task. We decided to evaluate our embedding to the one-hop question answering. What is one-hop question answering? We have a question which requires a simple answer from knowledge graph. For example, who is the son of Albert Einstein? Hermann Einstein is the son of Albert Einstein. One entity is an answer. So we provide a pipeline. We call this pipeline graph, text to graph. And in this pipeline, we map question embedding to the space of entity, relation, and entity, and counting cosine similarity of entity, relation, and entity in triple, we ranked all possible answers. So there is results for simple question data set, and we evaluate either different models, our models and KA QA models, and embedding models. Embedding we used in these models is Transio and PTBG. It is PyTorch big graph, Transio from PyTorch big graph. And our embedding Mikor and our embedding into our pipeline provides the best score. So concerning the Russia question answering, we do the same evaluation pipeline, and also our embedding under our model provides the best score. So as a result, we present a method for obtaining knowledge graph embedding, and this method is better for training on a smaller GPU card for restricted memory assumption, under the restricted memory assumption. The next chapter is about representation of the weight inside the fully connected layers, inside the big language models. So we have big language models, and there are several bottlenecks inside this language model: SMLP blocks, embeddings, and attention. So we see how many parameters are stored in MLP block, embeddings, and attention, and decided that, as you can see from this table for BERT, BART, and GPT-2, the most parameters are stored into the MLP block. So we decided to represent MLP block in a compressed way. And to do this, we select the tensor train matrix representation form. Tensor train matrix representation form is a more widespread form of tensor train format. What is tensor train format? In tensor train format, we have an n-dimensional tensor. In our case, it's three-dimensional tensor, and we represent this tensor in the set of three cores. Every chorus has dimension no more than 3. So if we want to calculate every element of the initial tensor, we take the corresponding slice of the first chorus on the second chorus on the third chorus, multiply it, and we obtain y digit, which is corresponding to 1 element. So core has inner core have 3 shapes, 2 ranks, and y other shapes, and adjustment core has 2 shapes. One rank is equal to 1, other rank which is equal to the next rank to the next core, and inner shapes. So there is an algorithm of the tensor train compression, how we obtain these cores, these factors. We have a tensor, and we unfold tensor over every axis, and into this unfolding, we apply SVD decomposition to every of this unfolding. Then we take factor U from SVD decomposition, reshape it to our core, to our first core or second or third. It depends on the axis over which we unfolded our initial tensor. And the multiplication of sigma and v factors gives us the next tensor, which we will unfold on the next step. So during this algorithm has number of steps which is equal to the number of dimensions in our tensor, and we obtain the set of our cores. Tensor train matrix is a more widespread version of tensor train. The difference is the tensor train represent tensor as a set of points, and tensor train matrix represent tensor as a set of matrix. So we work not with point but with matrix. Because of it, as matrix is described by two indexes, we set here not three-dimensional core but four-dimensional inner core. So from one index, we obtain two indexes. In other words, if we have matrix of fully connected layer with the shape dimension input multiplied to dimension output, we can factorize dimension input into the set of IM factors, dimension output of the set of GM factors, and I1 J1 will be the inner shape of the first core. So if we have these shapes and these ranks, we usually set all ranks of all the cores equal to one rank R for more easy computation and for more easy compression. We have proof compression rate, which is defined by this formula. And we, as you can see, compression rate depends on rank and square. So if we have, if we set rank not very high, we obtain a proof compression rate. But when we represent fully connected layer in the set of 4 cores with rank 16, we found this memory. We need to provide forward and backward operation. So the new layer based on TTM needs more memory than a regular fully connected layer. What is the issue? The issue was the following. When we represent our matrix as a set of cores, and we want to provide forward, for example, we should subsequently multiply our activation to every course. And we do it by torch obtain sum function. Torch obtain sum function provides scheduler which defines the order of the contraction. For example, we can firstly contract our activation to the last core, then to the third core, and so on and so forth. So PyTorch opt-in sum finds the optimal contraction, but optimum according to the memory, not according to according to the time, not according to the memory. So we decided fixed it, and we vary several approach to forward pass. We set scheduler by ourselves, or we used the scheduler which was provided by PyTorch default. And according to the backward pass, we notice that backward pass is also a contraction. And in the backward pass, we share intermediate result for the intermediate computations. And to the second approach, we say that also along the batch axis, in the transformer batch is batch size is sufficiently large. So over the batch axis, we provide the first convolution. And we vary this pair of approaches, and approach and sum, this is default PyTorch computation, and full matrix, this is storing the pre-computed, some pre-computed result, provides the best memory and best time. So the result of this chapter is that we present TTM linear layer, PyTorch compatible layers that can be used instead of fully connected layers, instead of the neural network in common and transformer in particular. So the next step is to see how this layer will behave inside the real model. We decided to train from scratch several GPT-like models. In the first models, we replace fully connected layer with TTM with some rank layers. So, for example, we select 4 cores, and the shape of this course will be this. And as a baseline, we set the replacement of fully correlated layer with SVD air structure. SVD air structure is a regular subsequent to linear layer without any activation between these, without any nonlinearities. Regular set of fully connected layer, one after each other, which is gone. So we provide several experiments. The first experiment was on Wikitext 0.3 dataset. It is quite small dataset, and in this dataset we train GPT small model with replacement, and we evaluate this model on the same dataset. And under this condition, we can see that we can compress, we can obtain a compression rate up to 40 without loss of perplexity. So it was kind of sandbox experiment because Wikitext is not very large data set. But this experiment shows that model with such type of layer can be trained. There are the set of experiments is about training on one type of data set, on more big data set. In our case, it was open web text like dataset, open web text, and we train two models from scratch by ourselves over the same condition, is TM72 and SVD50, and compare the result of this model on language modeling on Wikitext 0.3 to the OPT. OPT is a very good trained decoder-based transformer, which is trained on very high quality data to imitate behavior of GPT-3 with the with a number of parameters. And this distilled version of GPT is the GPT-2, which obtained by knowledge distillation. So we can see that, of course, the best score comes to OPT, but OPT has the largest number of parameters. The worst scores come to distilled GPT, but distilled GPT has the lowest number of parameters. And our model, which we train under the same condition, provide medium score, and among all algebraic-based model, TTM, which while we train it from scratch, provides the best score into the language modeling task. All data sets are in English too. We also evaluate our model on language understanding data on glue benchmark, and the tendency remains the same. The best score, the most of the best score, this is a task from glue, comes from OPT. The worst score comes from distilled GPT, and our model provides a medium score. TTM based model provides the best score than SVD based model. It will also evaluate our model based on matrix and tensor version of fully connected layers to the CNN mail dataset summary. Dataset of summary texts, and here our model is based on the Rouge1 and Rouge2. Rouge is a metric which describes the intersection of n-grams, and for Rouge-L, SVD-based model provides the best score. Outcomes that we evaluate the compressed model based on algebraic representation, TTM, SVD, distillation, and training from scratch the cut version of GPT-3, OPT. And among the compressed model, model with the highest number of parameters provides the best performance, and TTM provides the best performance among the algebraic representation methods. The next chapter is applying TTM decomposition. Decomposition in this case, in the previous chapter, it was training from scratch, and to the question answering problem. So in my thesis, I working with special case of question answering, which is called comparative question answering. Comparative question answering provides the question of type, what is better, X or Y with respect to Z. So there is an output of our demo, and in this demo we can see the special part of comparative questions: predicate, beta, aspect, deeper, and two objects for comparison, Python or MATLAB. The example is what is better for deploying Python or MATLAB, what is better for building cell or concrete or wood. And we evaluate, so we participate into the Touche shared task. The Touche shared task organizer provided the set of comparative questions, and we should retrieve from Clue Web Corpus the most suitable passages which fit the question from the questions. On the test phase, answers are assessed manually in 2 dimensions: relevance, how opportune and supportive answer is, and quality, how good studied and well understoodness of text. So data set we are working with is MS Merkle passage ranking, quite big data set for retrieval question answering. Retrieval means we retrieve question from some corpus. And unfortunately, this data set is for regular question answering, not for comparative. And we also use data set based on Touche. This data set contains of 40,000 of passages. It's not very high, but it's entirely comparative. So we evaluate several approaches, ensemble-based approaches, BERT-based approaches, and approaches based CalBERT. CalBERT is a special architecture based on BERT which provide late interaction. In ensemble models, we use random forest, XGBoost with special objective for retrieval, like GBM with special objectives for retrieval, and we use different features. Feature based on statistical language models, Chat search engine, relevance score, and comparative-based features, how many object, aspect, and predicates are in the retrieved passages. It's about comparative-based features. And this result for ensemble-based message, XGBoost provides the first according to relevance, first place, and second place according to the quality. And the next quite solid method is the CalBERT model. CalBERT model provides late interaction, as I previously mentioned. Late interaction means that instead of encoding query is a question, document is passage, encoding query document and calculate interaction of all token from query to all token from document, we do something like pooling. So we select token from document with large constant similarity to query and sum this score over the all query tokens. And this score sent to the MLP, and some MLP provide the best score, which defines how good our ranked passage is. So this is test result for CalBERT model. Is a quite good model, and for relevance, quality, and stance detection, CalBERT provide third place over the table, and we decided to compress fully connected layer into the BERT part of the CalBERT. But we decided to select proper layer for compression. We didn't compress all fully connected layer. We decided to select such layer that is more sensible for compression. For this, when we apply SVD TT to the matrix of the fully connected layer, we can see a gradual spectrum of every SVD. So this is this graphics depicts the spectrum of value into the SVD compression, and if gradual slope is less sharp, the layer will be uncompressible, and while gradual spectrum is more sharp, the layer will be compressible, and in more sharp spectrum we can define a rank by see the interaction point, reflection point, sorry. So there is result on MS Merkle data set, and we can see that if we select layer which is sensible for compression, we provide the best score. Then if we compress all fully connected layer, that we match into our architecture. And when we evaluate our data on Touche validation set, we can see that quality remains the same and relevance quality remains the same, but TTM compression is slightly better, and relevance remains the same to the SVD compression and TTM compression. So there is output of CalBERT model. On the left column there is passages which is retrieved by CalBERT for the question, for the query, what are the best rice cookers? medium column is a Calvert with compressed SVD layer, which passage are retrieved by this model. And on the last column, there are passages which are retrieved by Calvert model with compressed TTM layer. So you can see that quality is about the same. So of course, pre-trained Calvert provides the best quality. But SVD and TTM, I have no difference in quality. So the outcome of this chapter is that we apply SVD and TTM decomposition to fully connected layer in the Calvert model. Both methods give approximately the same result, and selecting more sensitive layers for compression can improve the performance of the compressed model. The last chapter is applying TTM and SVD to BERT and BART architectures of transformer. So in this set of experiments, we decided to apply SVD-based layer and TTM-based layer to the fully connected layers inside the two architecture, inside the two model, BERT and BART. And we decided to do it, we decided to fix 3 compression rate. So 53 million, that's approximately half of the model, 69 million at approximately 0.75 of model, and 102 millions is a very low compression rate. And this table represents the ranks for SVD and TTM, which we should use to obtain this compression rate. So as we compress yet pre-trained model, of course, we have drop in quality. You could see it in the previous chapter. And we decided to improve this drop in quality by adding Fisher information into the decomposition algorithm. What is Fisher information? This is Fisher information. And Fisher information is an expectation of partial derivatives of probability of output of every elements into dataset. D is a dataset, set of objects on which we will evaluate or train, with respect to W. W is the weight of the current layers. So we have fully connected layers, and for this fully connected layer matrix, we can calculate the matrix of Fisher information with the same size, which can be calculated by this formula, where W is the weights for these matrices. We apply 4 different methods. The first is SVD. We replace fully connected layer with SVD representation. Fisher-weighted SVD replace fully connected layer with SVD representation and use Fisher information. TTM the same for TTM, and Fisher-weighted TTM is the TTM with Fisher information. To use Fisher information, we should calculate Fisher information. This approximation of this formula are derived from the initial paper, and we can approximate matrix of Fisher information as partial derivative of loss over the one object with respect to weight of our matrix. So we should summarize these derivatives over all objects in data set and take an average. If we have this matrix, we can multiply it by left to the initial weight matrix, make SVD decomposition, and to obtain new factor U, we should apply by the left the inverted Fisher information matrix. This is formula for SVD decomposition, but for TTM decomposition, as you can understand, TTM decomposition is a set of SVD decomposition. So to apply Fisher information to the TTM, we should simply provide these steps inside to the every SVD decomposition inside our TT SVD. So this result. We have this result for glue benchmark for BERT model, and here we have on the every row we have particular method, and this method are grouped by compression rate. This 3 compression rate I've mentioned earlier. And there is our scores. And we can see that for small compression rate, for BERT, TTM and Fisher-weighted TTM provide the best score. But for when compression rate is grows, not growth increases, and number of parameters grows, SVD and Fisher-weighted SVD provide the best score. And we also can see that adding Fisher information to our decomposition always improves the score of the downstream task. The last model we evaluate under the same condition, 3 compression rates and 4 methods, is a BART model. And we evaluate BART. BART is a sequence-to-sequence model. So we evaluate it on the paraphrase task. What is paraphrase task? We have special data set, paradox. Paradox consists of phrase which is not in a proper way. Now I feel like a bad word. And we want to generate paraphrase which is more reliable. Now I feel like worthless, for example. And we have 4 metrics for this data set: style transfer accuracy, similarity, fluency of the generated text, and G is a joint metric. It's regular multiplication of star, similarity, and fluency. And we can see that for BART, for every compression rate, SVD and especially Fisher-weighted SVD always provide the best score. So there is a picture which describes the performance on every task in GLUE data set with respect to the compression rate. So here we have a compression rate on this axis, and here we have performance. Of course, we have different type of performance, different types of score for every task in GLUE benchmark. So this is SST, and this is the average score of GLUE. And we can see that feed-forward SVD is the best. SVD with Fisher-weighted. So as outcome, we compare different technique for compression of fully connected layers in BERT and BART models. At different compression levels, different technique can give better and worse result. And the alignment of the task and the decomposition objective, the alignment of these 2 objectives significantly improves the performance of the compressed model. As a conclusion, we can see that we stated several statements into the objective, and we successfully use canonical pleiadic decomposition in compressing the embedding of knowledge graph units with increasing quality. And tensor train matrix structure can be used into the to represent weight matrices of fully connected layers. And while we train model with such type of layers from scratch, TTM-based model based on TTM fully connected layers provides the best score than SVD. And compressing yet pre-trained transformers, not trained from scratch, but compressing, gives the worst result. And TTM compression has superior result compared to SVD only in the higher compression rate, only in one model, BERT. And overall, we can improve the performance of the compression model by selectively choosing compression-related layers and integrating task-specific objective information. For example, Fisher information into the decomposition algorithm. There is references, and this is all.
Okay. Viktoriia, thank you for a very nice presentation. So the next point is the questions from the jury members. So colleagues, please feel free to ask questions.
If anyone wants before me, I would like to step aside, but if I may. Could you please come back to the 17th slide of your presentation?
Okay. Okay, this is.
Yeah. I have a question. During describing this slide, you have mentioned that you haven't used the computational graph. What do you mean? What did you mean by this?
The regular approach to obtain the embedding into the neural network model is to represent it as embedding layer, and then we set some objectives, some laws, and we started to regular training process.
Okay.
But in our approach, we didn't do this because we can calculate gradients by this formula. And for counting this formula, we didn't need PyTorch computational graph. And when we use PyTorch computational graph, it can require more memory than usual method. And because of this, we have such low memory needs.
Okay. As far as I understand, what you're saying is that you're not using the PyTorch computational graph, but the computational graph itself you are actually using, because you cannot do not use the...
I suppose no, because when I say about using computational graph, I mean that we are calculating gradients on the current layer or current subject using some chain rule started from some laws.
Okay.
But in this case, we use no chain rule. We don't start from laws. We only have three matrices, and doing something with these three matrices, gradients.
Okay. Thank you. I have a few more questions, but please switch to the 18th slide.
18th.
The next one. Yeah. So my question is, why is the such increase in size? I mean, in size of the memory footprint for the maker. I mean, your method, in comparison to the previous slide. So in this slide, your method get like 22 gigabytes, and it's being roughly the same as the other methods, while on the previous slide it was like twice lower or something.
Here we use method which is use special PyTorch structure, PyTorch sparse embedding. And as I know, PyTorch sparse embedding specially developed with using some features of hardwares to reduce the size of embedding layer. So if you use this method, in this method, there are special structure for embedding, which provide you very low memory assumption, very low memory needs, no matter that we need PyTorch computational graph. More precisely, complex is a very simple method. So complex is you have only three vectors and you multiply it vector by vector, and your loss is a result of this multiplication. So besides of sparse embedding, this method has a very short computational graph in PyTorch.
Okay, I see. Thank you. My next question is about slide 28.
28.
Yeah. Yeah. Could you please maybe give a bit more details why the TTM method is such huge, while the fully connected one is only 400 megabytes?
Okay. TTM requires convolution of activation and core tensor, subsequently or not subsequently. The schedule is the order of convolution is defined by this function. This function. And this function is built in PyTorch function, and this function seeks the optimum scheduler optimum order for time. And as I understand, for this rank, particularly for this rank, it's turned out that optimum time provide, for example, convolution of very large tensor with very large tensor, which require more memory.
Mm-hmm.
So if I explain it very easy, you have set of 4 tensors, and you have activation, and you should convolve. You should force activations go through all tensors, and I suppose that Torch OptSum decided that if we stacked all tensor in one big tensor, it will be faster. But it really be faster, but concerning the memory, it requires more memory.
I see. Thank you. My next question is about slide 52.
Okay.
The next one. Actually, maybe I missed something. That was like a table with glue results. Maybe it's some next. Yeah, the 53. Sorry. Yeah. Could you please hypothesize why the why all the methods has such low results on Cola dataset? They are like almost zero for most of the models.
Cola is a corpus of language acceptability, and this is a data set which on which we can say either the text, either the sentence in English is linguistically correct or not. And I suppose this task is quite difficult for the compressed version of model. So when we compress model, we lose some information about language and some unimportant information, less important. And maybe compression algorithm decided that information about grammatically correctness of some text, of some sentences is less important than, for example, information about generating words. So it's very easy explanation, but more formally, we did several experiments on glue, and yes, when we compressed model on Cola, so the first data set in glue where we started to lose our quality is Cola.
Yeah, I understand. Can we like conclude from these data that for linguistic acceptability, all the weights are important, almost all the weights? What do you think? I'm not like require you to make a statement, just your opinion.
My opinion is that yes, information which needs to resolve linguistic acceptability good is treated as less important by some decomposition algorithm. But of course, maybe in further research, we can add something to the decomposition algorithm which set to this information more high weight. And we can provide some TTM special for Cola decomposition, which will not lose quality on Cola.
Okay.
But now, yes.
Okay, thank you. That's it from my questions. Thank you.
Dear jury members, any other questions? Okay, maybe, so do we have...
Actually, we have raised hand from
Maybe.
Professor
Can I just ask, can you hear me?
Yes.
Hello? Yes, perfect. So I have a few questions, but probably we'll start with the one. So I think this question was asked by Pavan in his report, but I'm interested in that as well. So I didn't see in the thesis any like motivation why, from the practical point of view, why should I use compression, like the TTM compression of the models, instead of simply reducing the number of parameters, right? So what are the benefits of this, and what are the advantages of employing TTM compression instead of just making the model of base size instead of large, or small size instead of base? And if we look at the tables in chapter 7, the results of the compressed models are not that significantly different from, for example, the results of Distelbert or the results of FP16 evaluation. So why?
As if I understand correctly, the question is why among all methods for compressing number of parameters, for example, pruning, distillation, and tensor-based or matrix-based method, I choose tensor-based. The issue was that for obtaining a good result on distillation or pruning, you should deeply investigate their pipeline of training. So you should change the training pipeline significantly. This is the first point. And the second point, you should provide if you want best result, you should provide a more high you should provide data set with more high quality. And and if you use compression, if you replace layer to its compression analog, you cannot change training pipeline, and so you can do the same things that you can do for training GPT small, and you shouldn't pay a lot of attention on training and to collection data set. And this was a case that was tried to represent modulus of transformers into the tensor or matrix way. And other point is curiosity. It was interesting, is fully connected layer can be compressible or not?
Yeah, I mean, it's the curiosity is, of course, a great reason alone. So even if it is just scientific curiosity, that's already enough. My question was more of a practical nature. So, like, imagine that you you would like to reduce the model, like to compress the model. So, would you still recommend to NLP practitioners to use TTM compression instead of just quantization of the whole model, for example? Or
if you have a department of NLP researchers that can sit and investigate new training pipeline and try every new application for training, and trying some tips for training, and have time and have person. If you have time and you have persons, it is better, of course, to try and train from scratch under the more accurate conditions. But if you have limited resources and limited number of person, it is better to use TTM or S3 decomposition, as far as I understand.
Okay,
depends on environment.
Okay, so thank you. Another question. So I remember that some jury members raised hands, so we can just switch to them.
Yes. So, Dr. Egger,
Yeah.
you would like to proceed?
Yeah, thank you very much for the presentation. So I have like 2-3 questions. The first one, if you go to if you go to slide number 34. Okay, yeah, thanks a lot. So here, so in this table, you have like 5 models, and then if you go to slide number 35. Okay, so here you also have 5 models. If you go to 36. Yeah, so for the text summarization, only 3 models remain. So I asked the same question in the on your initial version of the thesis. So can you explain why only 3 models are remaining here?
Yes, it was a great point that all of this table should contain the similar number of models. And initially, we have no opt in the natural language understanding. And while I received your remarks of jury members, I have time to provide experiment with opt for natural language understanding, but unfortunately I have no time to provide experiment for opt and still GPT for daily mail summary. So we partially fixed this point. We set the same set of model for the natural language understanding, but have no time, unfortunately, to add model to text summarization. This is only the point is only limited of time, but I assume I agree that it's better to compare all this model under the text summarization pipeline too.
Okay, thank you very much. So basically, for the paper that you submitted, you just did not have enough time to run all the models on all the data sets.
Yes, basically we want to compare GPT-2 based on TTM and SVD because this model we can train from scratch by ourselves, and it was clear comparison. And and when I obtained notice about that all baseline should be in all table, I decided that yes, it's true, and try to reach up all table, but have time only for one table.
Okay, thank you. And the second question that I have is, is not a technical question, more out of curiosity. So the first paper you, so that's the maker paper or the maker model, you submitted that to the student research workshop. So could you give an explanation why did you submit it to the student research workshop at ACL rather than to the main conference, and maybe also what were the reviews of this paper?
So as far as I know, student research workshop is ranked as a main conference, and we choose this event because up to the corresponding deadline, we have some material. So we can't fit the deadline of the main conference, but when deadline of student research workshop is come, we have sufficient material to accept it high quality paper, so we decided to submit it here.
Okay, it was just a matter of the deadline.
Yes.
And actually, out of curiosity, do you know if there's a difference in the? So what's the difference between the student research workshop and the main conference?
As I know, I can be wrong, but inside the ACL there is no difference in ranking. But maybe somebody correct me. So student research workshop is ranked as the main conference.
Okay, cool. Good to know. And the last question from me would be more of a general question. So you have now your particular approach to efficiency, but there are other approaches like distillation, quantization, etc. So can you maybe go a little bit into the difference of these different techniques and what are the advantages and disadvantages? Can you say something on this?
Yes, of course. I can go through. So, yeah, am I understand correctly? You want a brief discuss of advantages and disadvantages of distillation and quantization, yes? Or something else?
Yeah, sorry. Yeah, exactly. Distillation, quantization, and your approach. So which one is better? Which one should I recommend to my students? What are disadvantages and advantages of those approaches? If you can say something on.
So yes, I can. It depends on environment, and it depends on environments in which you want to run your task, run your compression. Distillation technique can be very high performative, but you should be very accurate with training pipeline. As you know, into distillation, you have several additional parameters for training. For example, weight with which we can add to the main loss the chiral divergence loss at the target loss, and this weight you should also tune. And as I can see practically, besides that is out of scope of this presentation, distillation can achieve very high performance if you are very accurate and spend a lot of time to fine-tune training process. Quantization is so quantization is also can be high performative, but as far as I know, now you can simply cast into the PyTorch your model to FP16, and your model your model does not provide very high drop in quality. But if you try to quantize transformers by ourselves, by hands, you can obtain not very high score, and you can add to the quantization some task-aware term to improve your new quantized weight in the way that can help model to fit better on the task you want to on which you want to run your model. By the way, distillation and quantization can suffer from, if you have a very good model, which is quite good on few short learning or zero short learning, when you apply quantization and distillation, it can be a case that you obtain quite good score on language modeling, but score on few short and zero short learning can be very low. And this is a case that I've seen practically. So I can't give any advice which method you want to use, but the main point is that distillation can be good, but it requires more attention on training. Quantization is also be good, but it requires more attention on some not language modeling task or few short or zero short pipelining. And TTM SVD also can be good, but it requires some fine tuning. But the plus of TTM and or SVD compression is that fine tuning pipeline, you can't investigate a new train of fine tuning pipeline. You also can train or fine tune TTM based or SVD based model like it is regular model.
Okay, thank you very much.
Okay, so I think Dr. Shalmanov raised the hand, right? So we give a word to him.
Yes, thanks. My question is actually from the review. But first thing first, I want to ask, like, if we go to this slide 36, and we can see that actually the different methods provide different compression ratios. But the question is, like, what if we compare apples to apples? Like, if we compare the same compression rate with your method with Distill GPT? What will happen? Will we get any improvements over Distill GPT or not?
Can you please repeat question? You asked about if we can we obtain distillation version of GPT with the same size as, for example, TTM or 3D, yeah, or no?
Yes, exactly.
So it will be a great point, and so it really will be a great point. But the problem is resources. For clear comparison, we should train all model from scratch under the same condition. But unfortunately, training one GPT-like model from scratch takes approximately 1 month on our machines. So we have time and resources to train only several models, and we decided to train model based on some tensor representation and to train model based on some matrix representation to compare it clearly, by honest, to say that yes, TTM S3D will be trained under the same condition. And unfortunately, we have additional resources to train other model by our lab from scratch. At this only point, we did not do it, but I agree with you that it will be very great if we can obtain distillation version of GPT with the same size, we can compare it.
All right, thanks. Another question is, okay, so your method gives some size reduction, like, well, basically any of them. But we also know from your experiments that FP16 also very good. Usually, if you just apply FP16, you'll have approximately same performance. Sometimes it's worse, sometimes it's better. But you also have a very good compression because FP16 is basically 50% less memory, or maybe 40% less memory. Why cannot we just apply your method and FP16 at the same time? What will happen?
I'm sorry, I'm hear you not very good, but I noticed that you asked about FP16, and for this I do some additional slide because oops.
If you want me to repeat question, I can change the microphone and maybe it will be better. Will it be better?
No, I understand question, but I want to scroll up the slides and I can't. Maybe can you scroll up to the end after the reference? There will be additional slide for Dr. Shalmanov. Before? Not before, maybe. Next slide. I can't. Yeah, here is our experiment. So we did experiments for FP16 for our industrial partner. The answer to your question is yes and no. No, because the message which we now have in FP16 is doesn't support the algebraic method we used to apply TTM decomposition, but we can firstly compress our model in FP32 and then cast it to FP16. And there is result that we done for our industrial partner into the August. This is a result for the two model GPT-2 and Rudolph. Rudolph is a Russian-based multidimensional transformer which takes images and text as an input. And you can see that when we firstly compress and then apply FP16, we obtain quite good compression to the whole model corresponding to the regular layer.
Okay, that's good. Actually, it shows that there's some potential to reduce the size of the model if we apply multiple techniques at the same time. Thanks. I have another question regarding attention. So as far as I understand that you mostly applied your method to the linear layers of transformer, but not to the attention layers. I mean, but in the attention layers, you also have linear layers, right? So why not to just apply your methods to the linear layers in attention?
Yes, we try to apply our method to attention block. So in attention block, there is linear layer. But this linear layer, in fact, is a stack of matrices for query, k, and value. And when we use TTM, when we represent matrix as a TTM structure, instead of applying TT-SVD algorithm, we should apply some shuffling operator. So before making TTM-SVD, you should shuffle elements from your matrix. And as I understand, when we shuffle elements of yet structured matrix, which is k, query, and value, you broke something into the attention. And because of it, yes, we applied our TTM representation to linear layer inside attention, but this provides very low score. And we decided not to mention it anywhere.
Well, I mean, that's also part of the research, right?
Yes.
Okay, thanks. So that's basically doesn't work. That's fine. So another question, what is the compute time overhead of inference of your TTM-based models?
Okay, we have other slide for Dr. Shulmanov. This is inference time and electricity consumption for GPT-2 model. And so the bottom table is about average forward-backward path time per batch and average power consumption. What can I see? We can set such TTM structure. So we set TTM structure, which we define the number of cores, when we define to shape of each chorus, when we define to rank of this chorus. So in this case, we can say that we set the structure. So for several TTM structure, we can obtain increase and decrease speed up of the inference time, but it's not stable for all TTM. So for some TTM, for example, for TTM with 3 cores, we obtain low speed of inference. For example, for TTM with 2 cores, we obtain speed up. And as you can see, if we have speed up, we have more power to compute in TTM, and it is not a good point for our TTM decomposition, for our TTM representation. So we can obtain speed up of inference, but this speed up is not stable over the selected structure. And for example, memory compression is stable, and for every TTM structure, we obtain compression in memory.
Okay, all right. But okay, some additional question. As far as I understood, that contraction, these operations between tensors in decomposed fully connected layer, it requires additional time. But how did you manage to speed up that? So you probably like due to better parallelization, or because you use some sort of like optimized schedule. So what is the source of this speed up here?
So this is not time for one layer. This is time for forward-backward path for the entire model.
Okay, but why it speeds up the network? Is there any guess why adding more operations results in faster compute?
I suppose I understand the question. It's expected that we have speed up always because in TTM we have less number of parameter, and if we should go through the less number of parameter, of course, we expected that we do it for the during less time than usual.
Yes, but we also need to do more operations between matrices. Doesn't it require more operations to do the computation, or you claim that it's actually less number of operations?
So concerning the number of operation, I suppose it's very strictly depend on the structure, on the TTM structure, and you can research, you can very accurately see to the scheduler of construction, and analyzing the scheduler, we can answer the question.
All right. Okay, I have a couple of questions, if you allow me. So, are there any previous works that apply this tensor train decomposition to neural networks?
Yes, we have very good work of Alexander Novikov, which apply TTM form to the embedding layer. And as far as I understand, it's all. So we have embedding layer in form of TTM and all, yes. But what should I notice in every case, for achieve better performance, you should train from scratch, either layer or full model or entire model.
Okay, and I think the last question is about this modification of TTM-based neural networks, which is called Fisher-weighted TTM. And you applied it only to models like BERT in your work. Is it possible to apply the same method, which looks really cool? It looks really good in terms of performance and trade-off between performance and compression. Is it possible to apply this method to GPT models?
Yes, because when we are talking about TTM, TTM shape, TTM structure, TTM decomposition, and TTM decomposition with some additional information, we are in the space of fully connected layers, and we can apply this method to every model which contains PyTorch fully connected layers.
But as far as I understand, you didn't provide the results with this method applied to GPT-like models, right?
Yes, because we so in my thesis we train GPT-like model from scratch, and we compress yet pre-train BERT and BART model. When you want to apply Fisher-weighted Fisher information, it is reasonable to apply it to the compression when we compressed yet pre-trained matrix. And as we did compression to the BERT and BART, we apply this to BERT and BART.
All right. So we can expect some improvements with this Fisher-weighted method if we apply to GPT compared to results that we have right now with the thesis, right? Or not?
We can expect of some improvements while applying this method while we train model from scratch. Because adding Fisher information helps us to find best decomposition among all possible. And when we train model from scratch, we didn't need to find decomposition. We set up some structure, and we fill the structure by meaning training it from some initial Gaussian value.
Okay, I see. All right, that's it. Thank you very much.
Okay, thank you. So any other questions from jury members?
Yeah, I can ask one question. Yeah.
Okay, please.
So Viktoriia, if you can go to your slide number 36 again.
26?
Or 36.
26.
No, 36, sorry. Yeah,
This one?
no. 36,
No?
36.
30?
Yeah.
This one?
Yeah, just following up on the previous question by Dr. We understand that it may not be possible to apply digital GPT with 62% compression ratio, but what about this TTM model with 23% compression ratio? Did you try that?
I'm sorry, can you repeat your question, because it's not very good connection, or maybe type it into the chat.
Sure, I'll type. So,
Perfect comparison with digital GPT.
So I understand. No, we haven't tried. As I mentioned earlier, we have only small number of model we can train from scratch, and this model will be this two TTM with this compression rate and SVD with the same compression rate. No, we didn't.
okay.
Sorry.
Got it. Yeah, that's all. Thanks.
But yes, so I can see your question. Yes, I agree that it will be a good point to compare all models with the same number of parameters with the same compression rate, but due to the lack of resources, we can't provide this experiment.
Okay, so any other questions? If not, then I will be the last one. Okay, seems no questions. Okay, Viktoriia, could you please open slide 12? So about this iterative algorithm, so do you have some guarantees here? So what, for example, if you change the order of these updates or do something else, can you obtain better? Do you have some theoretical results? Are there some better algorithms? Why do you choose it? So this is the main questions regarding, so some intuition, why do you choose this algorithm?
So this is the most popular algorithm for obtaining CP decomposition. It's quite widely used. If you change the order of updating ABC matrix, there is so it can't influence to the it haven't no influence to the result. And yes, we apply the CPLS version of this algorithm to our model to our knowledge base, which is represented as a tensor, but obtain not very good result. More precisely, we obtain hit at score approximately 1%, but here we have approximately 50 or 30%. So we decided to choose something else.
Okay. Okay, let's forget about this algorithm in this case. So the next question will be like this. So you use this tensor decomposition. So this question will intersect with the question of Dr. Shelmanov, but okay, let's ask it once again. So definitely you reduce the number of trainable parameters. So this is the purpose, but what about the number of computations actually? If you use this tensor decomposition, will it be smaller? I can believe in this also.
Flops, you mean?
So I mean just number of operations which you need to perform, like mathematical. So I don't need flops, but okay, how many operations do you need? Okay, not exact number, but will it be smaller in comparison to this full layer, or will it be bigger?
In my thesis, I try to approximate float and port operation of every method of forward and backward. In common case, there is, for some method, number of operation we need to obtain our decomposition. Not decomposition, we need to provide forward and backward, is not depend on tensor rank. In some issues, it depends on tensor rank. In some issue, it depends on square of tensor rank. And it depends on the method you choose for forward and for backward.
Okay, so it depends on the method. So the next question will be, okay, could you please open slide 39? Okay, slide is not so important, but before this slide, you told us about training from scratch, right? And I understand this problem well, so you reduce the number of trainable parameters to fit the memory, right, to be able to train. But then you start not training from scratch, but some fine-tuning or something like this, or just compression. So why do you need it actually? So what is the task? To compress the model or to fit to the memory on your GPU?
We compress the model in the both case, either we train from scratch or when we compress regularly pre-trained model. Of course, training from scratch is more clear way to compression. Is in this under this condition, your model with TTM layer provides the best score, but unfortunately, you usually have no resources to train from scratch, and you should compress yet pre-trained models and then fine-tune compressed model up to the task. And on the this chapter and on the next chapter, I provide several tasks toward which we can fine-tune our pre-trained transformer model, which was pre-trained and then compressed and then fine-tuned towards some task.
Okay, so the task was to train efficiently, right? Not to inference, to train.
Yes, the task. I suppose it's intersection between training and inference. So the task is obtain such model which require less memory on the training. Yes, concerning the tests on the training, but of course we hope that model require less memory on the inference too.
Okay. So the last question. So as a person with background from information theory, could you please explain once again the trick with Fisher information? Maybe some intuition. So could you please open slide 51? So, okay. 51. This is the formula.
51.
Okay,
Not
maybe. Okay, this one. Yes, this one. First of all, you have expectations of what is random. So what is D? Capital here.
D is a set of, so we have data set, and this data set as set of data is D, and dy is one object in this data set.
Okay, and the expectation is with respect to which random variable? So what is going on here?
As I understand this formula, we have some probability distribution, as our neural network predict probability distribution on the every object inside data set, and this formula describes how particular layer, weight inside the particular layer affects to the output of the neural network on the particular particular object inside the data set. And having this information, we can represent, compress, decompose our weights more efficiently, something like this.
Okay, but okay, a neural network is some deterministic function, right?
Yes.
How to introduce randomness in it? So I just
Why random?
so our input is random. What is random? So to calculate expectation, you need some random variable, right?
So I suppose expectation here means probability. So probability, integral of probability over the parameter over which we calculate this probability. No?
Okay, yes, probability, but on data set given weight. Okay, let it be. And so the last, why Fisher information? Why not, for example, just usual mutual information, or for example, some another? So is there some intuition? So I just, it is general question. I understand that you generalized it from some good paper, right? So for SVD, you just transferred it to your research, but what was the intuition there? So why Fisher information? How did they explain it?
So it's for me because it's so we work with weight inside the layer, and Fisher information make a bind, make a connection between this parameter inside the layer to the output, and output influence on task or the loss on the task, and so because Fisher information create a connection between this type of units, and we can use it to we can use it in this way to align two objectives.
Okay. In any case, it will be interesting to discuss it after. So thank you for your answers. So are there any more questions from the jury members? So not from the audience yet, because we have, or we finished?
Yes, I do have one question. Sorry. Yes, so just a very high-level question, which I already asked in the report. It concerns chapter 3 of your thesis, which is called efficient knowledge embedding using canonical polyadic decomposition. And it's not about the content of this chapter, but more about how it fits into the whole thesis. Because I might be wrong, but to me it really feels like an outlier. Like it doesn't. Like, what's the? Can you maybe explain what is the connection of chapter 3 to the rest of the chapters, and why it is even needed to get your message through? Like, will the thesis be worse without this chapter?
Chapter 3 is an efficient representation of data, and other chapters.
Using canonical polyadic decomposition. Yeah.
So the idea of thesis is to represent in efficient way some data, and this data can be a data set, can be a knowledge graph, and can be some parameters inside the language models. So in chapter 3, we represent data as a knowledge graph data, and other chapter we represent data in different transformer model inside the modules of different transformer models. But entirely, all of these are a representation of some big information into the some tensor form.
Well, okay, I'd say we probably represent information in tensor form in pretty much any NLP system nowadays, but yeah, okay, thanks. Thank you.
Yes, of course, but it's not compressed form.
Okay, thanks. I'm done then. Thank you.
Okay, so if no more questions, so we have important formal procedure. So each jury member should confirm that he is satisfied with the changes in the thesis, or just ask questions regarding the changes. So I suggest to do it in just, I will ask each member, it will be faster in my opinion and clear. So, okay, first of all, I will start, so I can start with myself. So I'm satisfied, so I confirm it. So the next one is Professor Egger. So are you satisfied with the changes?
Yeah, so there was this one thing about 2 missing entries, but yes, so yeah, so if they are not available due to computational reasons, I can say I'm satisfied.
Okay, thank you. So, Professor Kutuzov, so are you satisfied?
Yes, I'm satisfied with the changes. Yes.
Okay, Professor Goyal, so are you satisfied with the changes?
We can hear you.
Yeah, we cannot hear.
Maybe you could type it in chat. Yes, Professor Gayal confirms that he said it.
Okay, Professor Shelmanov, so are you satisfied with the changes?
Yes, I'm satisfied. There are some changes that she couldn't make into the thesis due to my review was a little bit late, but overall, I think that's a good changes.
And Professor Malых, so
Yes, I satisfied.
okay, seems we did it. So Elena, is it okay? Okay, good. So for now, we wait, or we expect the questions from the audience. So it is both which are offline and from online. So do you have some questions? If you have questions, please feel free to ask. It's not mandatory, but if you have. Seems no more questions. Then
I also see no questions online.
okay, good. So then we give a word to the supervisor, so Professor Alexander Panchenko, and so he will tell his opinion.
The general opinion about the dissertation.
I think you should speak about the student,
Yeah.
right, and do not speak about results. So it is like it is done in Russian Academy of Sciences. Here it's the same, right? Okay.
Okay. So just about the student, not about the graduation of the thesis. Okay. So what I should say, I met Viktoriia 4 years ago, first here, when she applied with many other students and was one of 3 students accepted. Was actually the first breed of students accepted to our group to form the BEDIS, and now at the kind of a doorstep of being hopefully graduated, and other students are graduated already. And during this time, Viktoriia contributed to a number of projects. First, she was a part of a Philips lab, then a part of a project with other companies, MTS and Huawei, and she was here around. She was really a big contributor to many activities, and I really appreciate it. She works with students, worked on different papers, led project. And a funny story about the topic of the thesis. We got strong expertise here on multilinear algebra, and I thought it would be nice to have the thesis on a collaborative topic on NLP plus Tensor, something like this. So because the topic interested me a lot, and so I suggested both 3 students, both 3 first PhD students, to attend a course on Tensor methods for here at Caltech. And they done it. So I thought at least one of you now need to do a PhD on this topic. Eventually, first the students didn't do it. And I'm really glad that at least Vika realized this suggestion and done a thesis somehow aligned with this expertise on something interrelated to NLP and Tensor multilinear algebra. I also know Vika as a person from day one who was deeply interested in neural networks, NLP, math, and intersections of all these fields and everything in between. So she is a very persistent individual, deeply interested in research in technical technical matters. And yeah, that's what I want to say. Maybe I leave some final words for later, but yes, that's what I need to say about.
Thank you, Professor Panchenko. And for now, as I understand, we should have voting. Elena,
yes, if I'm allowed to take up the procedure a little bit and help. So now we are ready to move to the closed part of the defense, which is deliberation and voting done only by the jury members. So all audience, you are most welcome to stay online. We will only move the jury members to a separate breakout room in the same meeting, and we will be back once the jury is ready with their decision. And all audience in class, you are also asked to leave the room, but you are most welcome to be back for the announcement of the results after the deliberation. Usually it doesn't take that long, so.
Okay, Elena is not here. Should I just announce the decision, right? Okay. Okay, Viktoriia, after some discussion, so it was, so the result is clear, but nevertheless we discussed the technical things, right? We decided to make a decision, accept with minor revision. So it means that within 10 days you should polish your thesis and upload it. So there will be no additional defense, right? So the defense is successful. So we don't have any opinion. So we think that you deserve the degree, but nevertheless we require you to do minor revision. So my congratulations, and we give a word to you just to say thank you to, for example, the secretary.
На выходе? Паченко.
So, Viktoriia, do you want to say something? Yes, of course.
And I'm deeply thankful to my friends who supported me on this way and support me now. So thank you very much.
Thank you, Viktoriia. So maybe last word. Okay, so the thesis is finished. Alexander, if you want, so please.
Yes, okay. So just let me now informally say a few words. First of all, I would like to thank colleagues who participated and helped to shape this thesis and the last steps of this thesis. I think your work and your contribution might not be underestimated. That really helped to finalize it. And I really thank you. So for Vika, I just would like to say that I'm sure that bright future lies behind you. And just think what you want to do as a next step. Make sure this is something you really want and really need, and that will make you actually happy. And then just go ahead and pursue this goal. And with your persistence, with your character, I'm absolutely sure that you will get what you want, and it will happen. So go ahead, don't stop, and that shall be just a trampoline for your future work, future career. Keep the bar high, and well, enjoy what you're doing and be happy along the side. So thanks.